at things that you guys aren't going to like very much just because kids don't like this name, I don't know why. But it's called an imaginary number. This does not mean they don't exist. This just means that in the real system, we don't have a way to deal with it. In particular, imaginary number, all it is a solution to this equation. It's a solution to this equation. This relatively simple looking equation, we don't have a solution for if you just use those real numbers. Does anyone know why? Why does that not have what's called real solution, Alex?
Because you'd have to square root a negative and nothing times itself is a negative.
Because you'd have to multiply something by itself to get a negative number. It's just not possible. Well, so what we've done and what mathematicians have done to handle this, I mean, you'd think that something this simple looking should have an answer. So since we don't have one in that system of numbers, we've created one. Which is kind of how square roots got invented in the first place. So it's similar to a square root in that we'll square root both sides. And you get x is equal to plus or minus square root of -1. And we symbolize this with the letter I for imaginary number. You symbolize it with the letter I. Number is a type of number that's non-real. What it is kind of a general way to write these imaginary numbers and real numbers together. And they are the following form. Complex numbers generally use the letter Z. I don't know why, that's just the convention. They letter it as Z, whatever. And they're equal to the following expression. A complex number is generally called, this label is Z, and it's written in the following form. It's A plus BI, or it could be some real part plus some part that's got an imaginary number attached to it. So something plus something else times square root of -1. A and B are just whatever numbers came up. You can write complex numbers however you so choose. I mean, you can just mix and match whatever real numbers you want to go in, toss in square root of -1, and you've got yourself a complex number. We'll talk more about those a little bit later. But try to use the quadratic formula. You got error, non-real answer. If you try to factor, it's impossible. It's going to let us solve some things that we just weren't able to deal with before. So like if I need to solve this expression, well, my algebra rules would say let's subtract 18. And get 2x squared equals -90. Divide both sides by 2, and get x squared is equal to -45. And at this point, you'd use a square root. And if you type this into a calculator, you get, it doesn't like you very much. It gets error im number, I don't remember what the exact error notation is. Yep. But if you use a square root, we can handle these using complex numbers or imaginary numbers. So we get x is equal to plus or minus square root of -45. Well, we can simplify this. Let's break this into some smaller parts. The negative, the first thing you probably want to peel off is the -1. So this is like plus or minus -1 times positive 45. Does 45 have any, say, perfect squares that go into it nice and evenly? 9 does. So what times 9 is 45? So -45 is the same as -1 for the negative sign. A perfect square, 9, and 9 times 5 gives us 45. So -45 and -1 times 9 times 5 are the same. Well, if we break these into 3 individual square roots and simplify, 2 of them we can reduce. What's this guy? That's just I. What's this guy?
3.
And this one's just still root 5. So the answer should be 3 times I times square root of 5 would be the most simplified form of this. We can use these to help solve equations that we couldn't before. You can also, when we're dealing with complex numbers in general, you can treat them you can treat i's just like a variable if you so chose. So if I ask you to add two complex numbers together, then you could treat this I like it's a variable, or like it's a square root. It's really more so it's a square root that we can't simplify. So we treat it like a square root can't simplify, so they'll sort of, kind of like unlike terms, and we'll combine the things that we can. So if I ask you to add these two complex numbers, 12 minus 11i and negative 8 plus 3i, well, we can add the real parts and add the imaginary parts. The real parts would be 12 plus negative 8. And the imaginary parts are what? Negative 11i plus 3i. And our new complex number we get is what? 4 plus negative 11i plus 3i's is negative 8i's. Or 4 minus 8i's. I added. Oh. Plus negative 8. 12 plus negative 8. Okay. And you can do the same. Combine like they just combine like terms. The complex parts, your final answer will be a real part plus a complex part. Or
What happened? Oh, so we're just like putting the eyes on one side?
you're combining like terms. Think of I like a variable, or more to it a square root, and add the terms that are like. The real parts, the imaginary parts. The real parts would be 15 minus 24 plus negative 9i's minus negative 9i's. You could distribute this negative sign into there. $15 minus 24 is negative 9. What's negative 9i minus negative 9i?
0.
Plus 0? Or just negative 9? Yeah?
Alright, so you have 15 minus 9i, and then you did 15 minus 24 plus?
Plus, and no, negative 9 minus negative 9. So negative 9 plus 9.
Did you read it? Did you distribute the negative?
You could have done plus and then negative, distribute the negative, and then still get negative plus a positive. Same number is 0. So you could say negative 9 plus 0 i's. And what's 0 times anything? Just 0, just itself. Just negative 9. You can think of distribute this negative sign. So change that to a plus and distribute a negative sign inside and combine like terms. Sure. These are a little more interesting. Negative 5i now times this. So we'll multiply some complex numbers. Well, distribute property still holds. So I'll distribute negative 5i to 8, which is what? Negative 40i's. What's negative 5i times negative 9i? What's a negative times a negative? Positive. What's 5 times 9?
45.
What's I times I? This expression is the same as squaring square root of negative 1. Or you end up with negative 40i plus 45 times negative 1.
So you can just square things
you're treating it just like a variable. So you can square a variable. Like you multiply something times itself. Why not? Because 5i times 9i should be square the variables. 45 times negative 1 is just negative 45. So in convention, we'll write the real part. Now there's no imaginary part here. This is not imaginary. This is all real. There's no square root of negative 1 anymore. It's all gone. It's just whole numbers. So we'll write the real part, the part with no imaginary numbers first. So 45 times negative 1 is negative 45 minus, this still has a square root of negative 1. Second. If you have two terms, how do you multiply binomials together? How would you if this was just an x, how would you multiply these together? FOIL. You chart multiply, whatever you want to do. You'll still do the same thing. The rules don't change. So, would you rather me FOIL this or use a box? Sure, we'll FOIL. First, negative 8 times 4 is what, negative 32? Negative 8 times negative 7i should be positive 56 i's. 2i times 4i is 8 i's. And 2i times negative 7 i's is negative 14 I squared. Just like if there were variables. Combine like terms. These are alike. What did we say was nice about I squared?
The terms of the coefficient.
What's square root of negative 1 squared? So this is really, say, negative 32 plus 56i plus 8i minus 14 times negative 1. Because I squared is negative 1. So we could change 14 times negative 1 is, so you just positive 14. And combine like terms. 32 and 14. Negative 32 and 14 is what? 18? Negative 18? 56i plus 8i's is what? 64? $64 would be your final answer. Still using FOIL, still using distributive property. Every solution to an equation that's complex gets us what's called a number's complex conjugate. So if, say, one of your answers is plus bi, then another solution that always is paired with it, it's called its conjugate, and I forgot what the notation is. It's like z, we'll call it z, this is probably terrible notation, but I'll call it z prime. Its complex conjugate, maybe we'll just call it zc. Now I'm getting picky, but the complex conjugate of this number is a minus bi. Oh, the conjugate of z, whatever it is a minus bi. Just flip the sign. Whatever it started with, give it the opposite sign between. It's the same thing as we did when we found conjugates last week to rationalize the denominator. We'll do this, it's the same idea. We'll multiply, say, if we want to get our quotient in standard form, we don't want square roots. I is a square root. If we don't want any of those down in the denominator, we can multiply by the complex conjugate to get and we should end up with something without square roots in the denominator. So like last week, if you think of this as square root of something, let's multiply by the conjugate. So multiply top and bottom. If it's minus 5i, we'll do plus I instead. Multiply by plus. And see what we get. So we're going to have to do FOIL twice, and you're just going to love it, I'm sure. FOIL. Well, 3 times 5 is 15. 3 times I is 3I. 4I times 5 is 20 I's. And 4I times I is 4I squared. Anywhere you see an I squared, it's the same as negative 1. So you have 25 minus negative 1, which is 26. And combine some like terms. 3I, let's see, 15 plus negative 4, because I squared is negative 1. 15 plus negative 4 is 11. 3I plus 20 I's are 23 I's. Complex plane is basically, we'll just do an XY plane. Just like we've graphed before, X and Y. Only the real parts will be graphed on the X, and the imaginary parts we'll graph it on the Y's. So if I ask you to graph a complex number, we'll think X's will represent like the real parts, and Y's will represent the imaginary parts. So if I give you a complex number like point A, say 4 plus 2I, I'll graph 4 on the real and 2, because that's the coefficient of my imaginary number. So point A would be at 4 reals and 2 imaginaries. B would be at negative 1 reals and 3 imaginaries. Negative 1 reals and 3 imaginaries. Would be B. Where's C gonna go? What's the real part? There is none. So we're not gonna go anywhere in the X. And we're gonna go 4 in the negative 4 in the imaginary direction. So 1, 2, 3, 4. And where does D go?
2 to the right.
2 real and negative 2 imaginary. Would be graphing these on what's called the complex plane. Okay. And that makes a kind of an odd shape. What's the absolute value of a number? What's that represent? Like if I have a real number, distance to 0, right? So the absolute value of an imaginary number is the distance to the origin. It's the distance to 0. The absolute value of an imaginary number is just its distance to 0. Well, shoot, how would you find the distance to 0 of, say, this imaginary number? What's a strategy you could do? Asking a thing now. How would I find how far this point is away from here? How would I find that distance? What's something you could do? Kim? You use distance formula. You could also, how about make a right triangle and think Pythagorean theorem? So the absolute value of a complex number is just Pythagorean theorem. The square root of a squared plus b squared. That's why we wrote it in that nice form. So the absolute value of a complex number is just Pythagorean theorem with the 2 coefficients. Square root of a squared plus b squared. Absolute value symbol. if I find the absolute value of z, which if I said z is equal to this complex number, the absolute value of this should be equal to the square root of 5 squared plus negative 12 squared. Or 25 plus 144. Again, if you have 25 plus 144, square root of 169, just 13. The absolute value of this complex number is 13. It's a distance of 13 units away from the origin. That's all it says.
Wait.
Your absolute value of any complex number will not have any i's in it. It'll be a whole number. It's a distance from 0. It's a distance from the origin. Okay, it won't have any complex numbers in it.
It's like, it doesn't look like.
Why is 5 plus 12 so